HARBEC partnered with Cornell, RIT, and Terrapin Bright Green through funding from NYSERDA to demonstrate high-performance, energy-efficient additive manufacturing. The management of HARBEC Inc. saw a need within their industry, plastic parts manufacturing, to improve upon the current design standards of conformally cooled plastic injection mold cavities. HARBEC wanted to look at the viability of utilizing biomimicry to see if cooling systems in nature can improve upon the current conformal cooling designs used in additively manufactured plastic injection mold cavities. Conformal cooling reduces cycle time for the production of plastic injection molded parts, reducing energy use and production time, saving both money and the environment. Through our partnerships with NYSERDA, RIT, Cornell, and Terrapin Bright Green, we were able to gain a number of perspectives on implementing the use of biomimicry in injection molds. Biomimicry is an approach to innovation that seeks sustainable solutions to human challenges by emulating nature's time-tested patterns and strategies. The goal is to create products, processes, and policies, new ways of living, that are well adapted to life on Earth over the long haul. Terrapin Bright Green reported in Tapping into Nature that bio-inspired innovation could account for approximately $425 billion of the U.S. GDP by 2030. DMLS is the acronym for Direct Metal Laser Sintering. The DMLS process uses a laser to melt powder to grow an item one layer at a time, effectively laser welding on a larger scale. Conformal cooling is a method for creating cooling lines that follow the contour of the molded part. This allows for faster cooling and more consistency in molded parts. Also increases the cooling surface area as well as providing even cooling to the entire mold cavity. This video shows the DMLS machine scanning a cross-sectional layer and the recoder arm applying the next layer of material. HARBEC reviewed a number of natural cooling systems to determine the best suited for the study. The systems reviewed were capillary action in plants, convection cooling in termite mounds, large thin animal ears that act as heat-sinking fins, and vein structures found in the mammalian vascular systems and in leaves. Capillary action was eliminated due to the fact that current additive technology cannot physically manufacture capillary structures small enough to take advantage of the capillary action phenomenon. Convection cooling was eliminated because the use of air as a heat transfer media and not as a liquid makes it impractical to implement in a mold design. Large thin animal ears that act as heat-sinking fins were also eliminated due to the fact that the use of air as a heat transfer media and not a liquid makes it impractical to implement into a mold design. Vein structures found in the mammalian vascular systems and in leaves were selected. 4 configurations were selected for comparison: conventional cooling lines that represent industry standard drilled lines, 2 variations of standard conformal cooling lines to represent current DMLS capabilities, and die-cut cooling lines that were generated using biomimicry principles based on die-cut leaf vein structures. Aluminum was used for its higher thermal diffusivity over steel. Each block averaged 20 hours to build. A custom mold base was designed by HARBEC to use for the grant. Cavity blocks were machined to fit the mold base. Impression surfaces were lightly polished to ensure parts released cleanly from the molds. These photos show the DMLS aluminum molds after testing. The testing procedures included the standard process setting for polypropylene. Cooling time was chosen to be the tested variable. It was assumed that parts with inadequate cooling would measure out of tolerance. The parts with the lowest cooling time, while still remaining in tolerance, were used for each test run. After cooling times were determined, each version was run for 50 shots. Total energy consumption was recorded with a data logger. The biomimicry die-cut version shows a clear reduction in cycle time over all other versions tested. This table represents the anticipated press time and energy consumption over a 100,000 piece production run. it can be assumed that a savings of 6.65 days and over 250 kilowatt hours will be realized utilizing the Biomimicry die-cut cooling strategy over conventional cooling lines. The keys for industrial adoption include informing customers about the existence of conformal cooling technology and DMLS use for molds, to inform customers about the advantages and limitations of the DMLS process, and to teach mold designers how to properly design for conformal cooling. In this project, HARBEC was able to successfully incorporate biomimicry into manufacturing processes that yielded productivity and energy improvements. Additive manufacturing technologies can enable entirely novel ways to manufacture precision molds and parts using less material, energy, and resources. Once again, we'd like to thank Terrapin Bright Green, RIT, Cornell, and most importantly, NYSERDA for funding our research. Thank you.